I might possibly ask you a question like something like, determine which of the following could or could not be a planet out of the four groups. So if you find the t squared over r cubed ratio for all four, what would show you that one of the four is not actually a planet? How would you be able to see that from your answers if you calculate those values? What would be the indicating factor to tell you, oh, this actually isn't. This is probably just a moon going around there. This is only valid for planets in our solar system ourselves. What do you think? No? Yeah, just look for one that's different from the other four. Okay? So you see three are the same and one is different. That's 9.4 is a lot of theory. Kepler's laws. The concept of the velocity of the planet, the seasons, the area swept out, elliptical orbits, the sun is one of the focal points. Then 9193 was a lot of math. We had a couple formulas from 9193. We had the formula for circular motion, and we had the formula for gravity. And then from 8384, we had the formula for torque, and then the idea of rotational equilibrium, right? As opposed to force equilibrium. Any specific questions on the problem set first? Joe, go ahead.
I had a question at 84. I just wasn't sure what to do.
Do you have the?
I was thought of maybe.
Do you have the problem, Joe?
Yeah. It's,
Can you read it?
Yeah. The problem is Jill of the jungle swings on a vine 6.9 meters long. What is the tension in the vine if Jill, whose mass is 63 kilograms, is moving at 2.4 meters per second when the vine is vertical?
Okay. So let me start with saying we did this type of problem in class. So when you get to a part where you're stuck on that, use the model that we used in class, because we did almost the exact same problem in class actually. But in class we solved for the velocity, right? We tried to find the velocity that the rope can withstand before breaking. Now this problem, it says they're given the tension, right? And you're trying to find the tension in the rope and you're given the velocity?
Yes, you're trying to find the tension in the vine.
Okay.
Yeah.
What is this? I'll take a nap, sure. Not do it till Monday, but I'll take a nap. So, Joe, the approach is very similar to what we're talking about. So when we think about a person swinging through the bottom of a loop, what do we have that's pulling them upward, that's keeping them from actually falling?
Well, I mean,
Yeah, so what force is that again?
that would be, wouldn't that be normal? No, that would be...
Normal force is when the ground pushes back up. Remember, it's always a reaction from a surface. That's our normal force. What do we have for the vine? What's the, you got?
That would be force applied, like the...
Not applied, it's just another word. Tension. Remember tension? Anything that's a rope, anything that can be pulled taut, has tension in it. So in this case, the vine has tension in it. So that acts this way, right? But at that exact moment, the person's mass also pulls them down. And their mass creates weight, and that's mg pulling down. Now here's the actual vine. It's attached to a tree. I'm putting just simply some sort of a surface at the top, like a ceiling. Okay, but it's attached to something. So this is the actual rope. So this rope is the radius of the curvature in this problem. So that's what we're going to use for R. The length of the rope or the vine was probably given in the problem. Okay, think about it like this, as a circle. Anytime anything's swinging through any arc, you can extend it into a circle of your own. Even if it's not, if the person is not continuing along that whole path, you can still draw the circle that exists. So in this problem, we want to recognize that it's in circular motion. So we always start circular motion with this formula. Okay, that's the formula we're going to use for circular motion. And this is one that we showed. We said it's really F equals ma, but A, if you recall, is really V squared over R. So this is the first formula we really need to remember. And this is on your formula sheet. I think both of these are on your formula sheet. I know A equals V squared over R is on your formula sheet. I don't know if the one after that is. I think it is. I didn't have it there in the past, but I added it. So we have to consider the fact that that's the acceleration. That's what's taking place of A right here. And then what is this is the question. What do we do? Anybody remember? What do we do when it's circular motion for the sum of the forces? Can we talk about up and down? Can we talk about left and right? Is the object moving left and right and up and down? It's not. It's not moving only in one direction. It's not even like a parabolic shape. It's in circular motion. It's a specific type of curve. It's very unique. Parabolic motion, believe it or not, like projectile motion, is not the same as this. They're both curved, but that curvature changes. Think about a parabola, right? At the top, it's more curved. And then at the sides, what does it start to do? It starts to almost become like a line, right? It starts to move in a way that has less and less curvature. Circular motion is different than parabolic or projectile motion. So what do we do with the forces? Look.
The ones that are outside of the circle are positive.
Exactly right. Anything pointing inside the circle is positive. Anything pointing outside is negative. So let's go ahead and write Ft minus mg equals mv squared over r. And our goal in this problem is to find the tension in the vine, so we can solve for Ft by adding mg over. And you know what, Joe? I'm really glad you asked this, because we can talk about something now. Let's talk about this solution before we get a number. So, if my mass didn't really matter and I was swinging, I would still be pulling on the rope. And this would be like the pull on the rope without my mass mattering. Okay? Now, my mass matters, so it's in here as well. But this concept that the weight itself is pulling down out of the circle, and the weight is acting against the tension, what does it actually end up doing? It increases the tension. Take a look. The tension in the cable just from spinning. So remember in the lab? In the lab, we spun the object this way, right? And it was moving in this direction. So tension was always acting toward the center. Does everybody see what I'm saying right now? Tension was pulling toward the center of the spin. Weight was acting down, though. Not toward the center from the circle, not away from the center. Weight physically pulls down. So the weight doesn't affect the tension in the rope when you spin it this way. You with me still? So it's only about the speed. This is the only thing that affects the tension in the rope when you're spinning it this way. But when you spin it this way on the side, like Rodrigo did with the cup of water, when that happens, the weight not only acts on the body, but it acts against or outside the direction of the circle, and thus increasing the tension by that amount. So when you're spinning something like this, at the bottom is when it's going to break. And that's what we talked about in class already with the vine or with the rope. It's going to break at the bottom because at the bottom, what's happening? The weight is being added onto here. If we did the exact same problem at the top, do you remember what it became? At the very top? What does the free body diagram look like if I do this? And we did it, so if you want to look in your notes, you're welcome to look. Okay, at the very top, what does the free body diagram look like? Rodrigo, go.
Tension and mg was to the same side.
Agreed. There we go. Tension and weight are both pulling down from that location. Weight always pulls down. Tension changes direction. When at the bottom, the tension is pulling up. Yet at the top, the tension is pulling down because tension is always directed to the center of the circle, while your weight itself is always directed down. So my equation at the top becomes the following. And we did this in class, so you can refer to your notes if you want again. But I want you to recognize the difference. Now solve for tension at the top. What do you have to do to mg to solve for tension at the top now? How is this different? What are you doing with mg? Now you're subtracting it. And this is what you get. So this is really important, Joe. Great question. Because it brings up the theory here and the idea behind when you're at the bottom, there's more tension in the rope. Because it's not just the object spinning, but it's the object's weight as well. But at the top, it looks like, oh, you know what? The tension is actually less in the rope. And that's because the weight is already pulling down, isn't it? The weight is pulling toward the center of the circle. So that doesn't leave that much left for the tension. Remember, the object wants to stay in circular motion. So when it's at the top, its weight is like helping the tension. So you know what? The tension can be less because the weight is taking away from whatever is needed. This is what's needed at the top, but the weight is helping physically. So this is the difference in these two. And Joe, to finish it, you plug in here to find out what the tension was. Okay? But the idea here, the theory behind it, is useful because multiple choice, short answer, these concepts are definitely going to come up. Okay, they're definitely going to come up. So I want you to write in your notes that this is a different problem from the horizontal spinning. This is a vertical plane spinning problem. You can want to write that term down because it probably will show up. This is when you're spinning an object in the vertical plane. That means this, like Rodrigo did with the cup of water when he was doing this. But when you're doing this, you're spinning in the horizontal plane. It's a different problem because the weight has no effect on that problem. When you spin something over your head, you don't care about the weight because it's not acting toward the center or away from the center. It's just acting down. But the circle is this way. Okay, two different problems. What do we think for the next one? Yeah. Yeah.
So since this is vertical, then the horizontal is about 10.
Yeah.
Horizontal.
Yep. Exactly. Rubber stopper is that's spinning in the horizontal. Because think about it. If I were to make ever see those video games? I've talked about Dragon Ball Z a lot, right? So remember Dragon Ball Z? Anybody who knows Dragon Ball Z again? You remember Krillin? Does anybody remember Krillin? Does that name ring a bell? He was a little bald guy. He would create this thing called an energy disc. He would put his hand up above his hand, and you would see this washer kind of appear, like a disc. That's in the horizontal plane. But if he held his hand this way and the little circle appeared this way, that's in the vertical plane. Okay? So you understand planes.
Can you go to 89?
Sure. What page is it? Do you know?
302.
Thank you. This is page 30289. All right, so let's see. We're in static equilibrium, the topic, right? So this is 8.4, static equilibrium, the concept of torque. So we're looking at a schoolyard teeter-totter with a total length of 5.2 meters and a mass of 38 kilograms. It's pivoted at the center. So here's our pivot point right there. If it's 5.2 meters, each side is 2.6 meters. I'm going to label that for now. It says a 19 kilogram child sits at one end. So that's the weight of the child right there. Right away, recognize, right? They're giving you the mass, multiply by 9.81 to get the weight. You're told the mass of the actual teeter-totter. But here's the thing. When you have an object that is isotropic, meaning it's the same throughout, like wood is not isotropic. If you look at wood, you can see the grains, right? The different grains have different densities, actually. So wood is a non-isotropic material, but this desk is made up of one substance the whole way throughout. When that is the case, and for all cases in our problems, we're going to assume that's the case, we can say that the weight of that object acts from the center down. So for the desk, the weight would act from right here downward, even though obviously it's not, right? It's really the weight is on the four corners, technically, because if we look at this floor. But for this problem, we assume the weight of the teeter-totter pulls down from here. And that has a mass of 38 kilograms, so its weight is 38 times 9.81. So we've got those two drawn. And then the last thing we're asked is this. Where should a parent push vertically downward with a force of 210? Where? So I'm going to put it anywhere for now. And that's 210 newtons. And I'm going to put here, I'm going to put R equals question mark. So really this time, the 2.6 is not going to come into play here. Because we don't know what the distance is. And the question says, so that it's, to hold it level or stationary. So the concept here is to use torque equilibrium. A torque pushing in the positive direction, or in this case, we did positive as counterclockwise, would be balanced by a torque pushing in the negative rotational direction, or clockwise. So this torque on the left of 210, which way would it rotate as a result of the 210? Push down on the left side? Counterclockwise, good. So this is going to produce a positive torque, and this will produce a negative torque. And we only have two torques acting. Why is the one in the middle, why does the one in the middle not matter, James?
Because it's pushing directly in the middle, so it's not pushing on either side.
Correct. So is it going to turn it? No, because the R value is equal to, R equals, use math. 0. R is the distance between the rotational point and the applied force. So if I apply force on the rotational point, what's the distance between my hand and my other hand right now? 0. I'm literally touching my other hand, right? But if the force is out here, this is my distance now. Do we see that, right? Okay? When I apply force on the rotation, it doesn't matter. That's why this red force, I said, won't really matter. Because the mass of the object and the weight of the object is really considered to be concentrated at its center of mass, which is the center of this object. Yes.
Why minus equal to or minus 4?
Because that's going to cause it to rotate, ready? Push down on the right side. That causes a clockwise rotation, and that is what we consider negative torque. Okay, if you forget, Aiden, how do we remember? This works, actually. I've been using it lately, believe it or not. Yeah, when there's one dash, make one slash. Or one C, make one dash. But when there's two C's, make two dashes. And believe it or not, that's actually been an easy way to remember for me. Right? I think did anybody figure out the mnemonic that Mr. D uses? Anyone? Because he's used it before, I just don't know what it is. So this does not affect the torque, so for now, let it go. All right, so as a result, let's see what we have. We're going to say we have 210 times its distance. What's the sine of the angle going to become here? Remember, we always multiply by sine of the angle? Sine of 90, which is equal to what? 1. So it doesn't matter here. And then it's going to be minus the other torque, which is 19 times 9.81 times the distance away, which is 2.6. And that has to equal what? Chris? Good. Again, we're looking to see that the seesaw, teeter-totter, same thing, is level. And level means balanced. It means rotational equilibrium. So we set the sum of the torques equal to 0. Hey, I might ask you a problem in the test that's similar to this, but doesn't say find the force or find the location of the force to cause equilibrium. Maybe it'll say figure out if the object is going to rotate or not. And in that case, you don't set this equal to 0. You figure out what the number is, and this would have a value, say 8, whatever, and you see what your answer is. If the answer is positive, it's going to rotate counterclockwise. If the answer you get from the sum of these is negative, it's going to rotate clockwise. So you can take the exact same problem and model in your mind with a different solution approach at the very end. Okay? Instead of setting equal to 0 and assuming equilibrium, the problem might say, or could say, will it rotate? And when you get next year to AP Physics, because I know some of you are definitely going to take that class, you'll not only talk about if it'll rotate, but then you'll take into consideration the actual mass of the actual teeter-totter. Because the mass is not really concentrated in the middle. It's distributed throughout. And that's going to be called a moment of inertia, and it'll relate to this. So this is going to go even further. But the concept that I'm teaching you now will continue to apply to any torque application, any rotational equilibrium application. Do I have to stop? Can I stop there? Is that good for this one? You get R? Okay, so solve for... So this is negative, right? So I would get a number for it and add it over here to start. And then I would just divide by 210. And that'll give you R equals... What do you get for R in the end?
2.3.
And that's logical because if you do the math, it looks like this number is less than 210, right? So it's got to be a little further out. So this number should have been a little shorter than the other one. Remember in the lab when we did that? So the answer is logical in its answer, in sense of number. Okay? It's a good question. Definitely a good question for the test. Both of those questions are perfect math type questions. And again, I'm trying to say to you that they can be varied, right? But the approach is really the same. The approach you're going to take is, analogous in nature between the problems. They're not any different there. What problem set?
Can you get 83?
83. Sure. So this says force to hold a baseball. This is page 302, number 83. A person holds a 1.42 Newton baseball in his hand. So that's what of the baseball? 1.42 Newton baseball. What is that about the baseball? It's good. It's already I think I said mass. It's already the mass times gravity. It's its weight, the weight physically. So just to give you a diagram, by the way. Here's the baseball right here at the end. And that's 1.42. Problem 83. 83 on page 302. It says that it's a distance of 34 centimeters from the elbow joint. So this distance here is 34 centimeters. Here's the elbow. And this is the shoulder. And here's the hand. Okay, so this is what you're doing right here. Make sense? It's the same thing as working out in a gym. It's a bicep curl. Literally, you're moving your arm up. All these things have many different applications, right? So although this is holding a baseball right now, it could be something else later. Holding grocery bags, right? I mean, it's literally the same thing. I'm trying to point this out right now because some of you on tests, I think, are having trouble with dissecting the problem. But think about what problem it's the same as. That's why we model problems. So if I give you a problem in the test where you're holding grocery bags, it's the exact same thing as this right now. Do you see that? Holding a baseball versus grocery bags. But it's just a different scenario. We're also told, let's see, the bicep attached at a distance of 2.75 centimeters from the elbow exerts an upward force. All right, so that's going to be a little interesting. Let's see. So here's the elbow. We have to kind of extend it in this dimension. And the bicep is exerting an upward force. And again, that's 12.6 newtons. And that distance is really small. I have to kind of like zoom in a little bit here. This distance right here is 2.75 centimeters. And this is all on the diagram, by the way. Okay, it's all on the diagram. I'm not just coming up with this. This would be hard to draw if you didn't have the diagram. I'm sorry, it's on the other side. See, and I'm drawing the diagram wrong. Put them on this side, please. Of course, can't erase that. All right. Finally, it says, there's some weight to your actual forearm. Calculate the net torque acting on the forearm and the hand. Use the elbow joint as the axis of rotation. And then finally, it says, if the net torque obtained in part A is a non-zero value, in which direction will the forearm rotate? So it's like the same exact problem now, but we're considering the fact that we have to think about what the overall torque is, not that it's in equilibrium. Consider the forearm and hand to have a uniform rod with a mass of 1.2 kilograms. So we draw the weight of the actual hand from the center down, and its mass is 1.2 kilograms, and that's times gravity. So this is a problem where the weight of the object itself, in this case the forearm, does matter. Because where do we draw the weight acting from? The center. And the center of where the weight acting is not the same as the elbow. The elbow is the axis of rotation. So let's draw in yellow here, like a node we call this. Right, a pin. Imagine taking a pin and fixing it right here. So you hammer a nail through and then this thing is allowed to rotate about it. Well, it's got some force that's pulling up, could be a rope pulling up, and another weight of the object is pulling down from here. And then maybe at the end, the flagpole outside this window is being held and there's something pulling on the end. So this is like a cantilevered beam. Okay, it's literally a flagpole sticking out of the wall is the exact same thing as this. But our question is find the overall torque. So we have got a couple things. 12.6, that'll cause rotation that's counterclockwise. That's that one. The 1.42 will cause clockwise, and the weight itself will cause clockwise. So clockwise is negative, the other one's positive. Joe?
Yeah, so I'm a little bit confused. How's the left side counterclockwise?
So this guy up here, you saying?
Yeah, because isn't the direction going upward?
So watch, ready? It's about rotation, not up or down, remember? Don't confuse up or down. Because last time it was upward, but it was on this side, wasn't it? And that's what caused clockwise rotation. Watch. Take your finger and push up on this object. Which way is it rotating?
Counterclockwise.
That's what you do. And these two, which way are they pushing?
Yeah.
So you push down, which causes this to rotate. Clockwise is negative, counterclockwise is positive. So I'm labeling the torques, not the direction of the force. Okay? And always do that. Seriously, on the test. Take your pencil, put it there, hold it where the axis pin is. You'll see a pin on there, always. You'll see where the rotation is. And then just literally do that, and you'll physically see which way it's moving. Okay?
Thank you.
So we have positive torque of 12.6 newtons at a distance of 2.75 centimeters. You know what I'm going to do? I'm going to use everything with centimeters here. Because if I think about it, what were the units of torque in the first place? Weren't they newtons times meters? So what's the difference? I could just make it newtons times centimeters for now. I'm not squaring it. I'm not doing anything like that. So I'm going to leave it all in centimeters for this problem. That's okay, actually. You can do that. As long as you express your answer as newtons times centimeters. I'm going to leave everything in centimeters.
That's what killed me for like 45 minutes.
You can leave it that way.
Accidentally.
Trying to change it. Which you could do that too, James. You could write 0.0275 meters. That's fine.
I kept messing up. No, I couldn't do it.
I get you. So the weight of the body Remember, the weight of the forearm is 1.2 times 9.81, and that's acting at a distance of 17 centimeters. It was shown in the diagram that it was the midpoint. Okay, so this is 17 centimeters right here in the diagram. And then finally, the baseball itself has a weight of 1.42, that's the force, times the distance of 34 centimeters. And that equals the net torque. Okay, see, pick up on this. The forces are here. See them? And it's force times distance, right? Force times distance, force times distance. And by distance, I mean length of the lever arm, R. But here, this is the force, because 1.2 is mass. Mass times gravity gives the weight, which is the overall force, times the 17. Right, here you go, go.
You can only use centimeters when it's stored, right?
Yeah. If we have other problems where we're looking at like F equals ma, and we're using acceleration, and acceleration is meters per second squared, we suddenly can't start using other units because they won't balance. But because this problem only involves Newton times meters for every single part of the problem, it's okay to use newtons times centimeters here. That's all right.
Express torque in newtons by centimeters.
Yep.
It's okay.
Yep. Absolutely. You could leave the answer in newtons times centimeters. So whatever this comes out to be in newtons times centimeters as my units. Okay, that'll give me my net torque.
What did people get?
What do people get for 83?
I'm at negative 7.33.
Negative 7.38.
I got negative 0.34. Yeah, negative 3.13.
3 different answers. 4 different answers.
No, I got negative.
Can we just do it now at this point? Right now that it's on the board, we could all just take a calculator out and check. So this is the right answer. So in newtons times centimeters. So it's possible that it might be 2 decimal spots off from one of yours. Because yours sounded very similar, guys. One was 3 point something, one was 0.03.
Yeah, negative 0.34.
Negative 0.3.
Negative 2.3. But
They sounded similar.
if it's used percentage, it wouldn't just be 2 decimals.
Yeah.
So negative 2.3.
Well, it depends on what the answer is. So somebody tell me what it is. Why are you shaking your head? Why are you shaking your head?
No, they wrote
Type it all in one
wrong.
line. All in one line. Guys, this could all be put in one line of code. Multiplication will occur by itself first on the calculator automatically. You don't even need parentheses. It'll all happen. Use time symbols now.
I got negative 2.13.
Negative 2.13?
Well, negative 2.13.
Negative 213? Okay. So negative 213. Sit down. Wise ass. Negative 213. It's fine. You should be happy you got it right. It's good. Good thing to celebrate. I'd rather celebrate that. Negative 213 newtons times centimeters. So if we did it in meters, as James said, negative 2.13. So what does that mean? It's negative, so it will rotate clockwise. Negative is clockwise, okay? And just look at the problem. It pretty much means that this person can't hold the baseball, right? That's what it means. It means the baseball is too heavy. So this is probably not, honestly, to me, a reasonable problem because it looks kind of like a grown man or woman's arm, and I think any grown man or woman could hold a baseball. So if it was a baby trying to hold a baseball, I think it would be more reasonable. But according to our answer, it's not going to be able to be held at all. Okay? Other questions, problem set wide? I'm happy to go over the stuff and I can talk, but I'd rather take your questions because these are the things you're confused on. Yeah, Aiden. 59. Do you know the page, Aiden? It's probably right before it, actually. Hold on. Okay. 3 what? 59 on 336. Oh, it's the next section. Thank you. Thanks, man. All right. Okay. Hey, another great question. You guys are like picking questions out that are perfect for this test. Wow. I made the test last night. That's why I'm thinking about it. So we've got a setup here, right, where there's a moon in the middle, the earth on the right, the sun on the left. That's pretty much what's happening here. And this is the earth's moon. Okay, this doesn't happen often, by the way. This is only at new moon. New moon. Okay, that's when you can see the full moon or no moon. Which one is it? Who knows their earth signs well? I don't remember, to be honest. New moon is when either you see a full moon or no moon at all, I think.
Isn't it now just the sun doesn't pass?
The whole idea is that the sun is right behind the moon, right? So therefore, yeah, the sun would be blocked by the moon, so the moon would be in darkness, so you would see no moon. That's good derivation, James. I like that. Right? Wouldn't that make sense? Because the light would be behind the moon and the moon would be blocking it.
Yeah. Does that happen monthly?
It says at new moon, the earth, moon, and sun are in a line as shown in this figure. So monthly, yeah? New moon has every month, right? 30 days. Find the direction and magnitude of the net gravitational force exerted on the moon. On the moon. So what is this? Give me an analogy to another situation that this is. Has nothing to do with gravitational pull, though. Come on, think about it. Think about it the last couple weeks here at Loyola. What could point out in your mind that is exactly this scenario? Net pull on an object. Chris?
Torque.
What is it? Similar to torque, but not torque. I'm thinking more school-wide. There's something that could be an exact example of this, Joe. Tug of war. This is a tug of war. Do you see what I'm talking about with the analogies, right? This is a tug of war. The moon is the middle of the rope. The earth is pulling on one side, and the sun is pulling on the other. So what do we have to calculate? How many different forces here? Now that you think of the analogy, it's easy. How many forces do I need to look for? Two. And whichever one is bigger is the winner. Do you see what I'm saying? Make some sort of reasonable idea. So this is literally one object being pulled in two directions. So if we draw a free body diagram of the moon to think about the net force, we could say the force on the moon from the earth and the force on the moon from the sun. That's the free body diagram of the moon. The moon is in the middle. Not really in the middle physically, but in this case, in between. How do I do this stuff, right? I don't have anything else. Well, you've got all the constants in the world. So at this problem, you need to go to your textbook and find a table, or just Google it. Okay? On the test, you'll be given the values you need, so don't worry. I'll tell you the mass of the objects. Capital G is given on the formula sheet, but it's easy to remember. 667, 10 to the negative 11. It runs. Okay? It's really easy to remember capital G. 667, 10 to the negative 11. But it's 6.67, I should say. Sorry.
So for this, when they said new moon, they just meant the moon.
Yeah, it's called the new moon.
I was so confused. I was like, why is it called moon?
Just use the diagram next time, right?
Yeah, I was like,
think about the diagram. Forget the problem in that case. By the way, whenever you get a diagram, you can almost ignore it. I think that's funny too. I think that's pretty funny. Yeah. So the force on the moon from the sun is going to be 6.67 times 10 to the negative 11 times the mass of the moon times the mass of the sun all over the distance between the moon and the sun squared. That'll give me the force on the moon from the sun. And that'll be a negative answer, right? I don't have to put negative right now, but I think about pull to the left as negative. So later when I do F net at the bottom, it's going to be the pull from the earth minus the pull from the sun. But now I still have to find the pull from the earth. And that's also going to be 667 times 10 to the negative 11 times the mass of the moon times the mass of the earth all over the distance between the moon and the earth squared. Okay, and that is usually given in a table as average distance between the two bodies. Okay, what should you really do to find those values exactly? What did we talk about in class? What did we talk about? For big celestial bodies, what do you have to really do? Take the radius into account. It's very minimal when you think about the average distance, though. Can somebody Google that for me real quick, or somebody have it actually? What's the average distance between the moon and the sun? The moon and the sun, because that's what we have to actually use as a value here. There's nothing else we can use. You have to find the distance between the moon and the sun, right?
Wait, I have.
It's not in the diagram, so you have to look it up. So I'm
I
saying.
think it's 1.5 times 10 to the 11.
All right, so let's write that down for a second. So this denominator is going to be 1.5 times 10 to the 11. Now, what's the radius of the sun and the radius of the moon? Can we look those up also? Because that's the real distance between them, right? The average distance between them in your text is not referring center to center, unless it says center to center. If it says average distance between, it's usually referring to surface to surface. I should actually check on that, actually. Now that I'm thinking about it, I don't know if new texts account for the radius or not. But when I'm doing these problems, that's what I think of. But I don't think it's actually significant in this problem. It might be between the Earth and the Moon.
When I was trying to find total distance, I got it was 1,474,000, or 14,743,367.
That's what you're getting as a number?
Yeah,
Between the Moon and the Sun?
yeah.
Yeah, this number is way bigger, right? Yours is on the order of 10 to the 6 or 7. It's on the order of 10 to the 11.
Yeah.
So something's up with those numbers. Can you just give me a number for the radius?
Fucking radius of the sun,
Yeah.
695, 700 kilometers. So
695, 700, and then kilometers, so 3 more zeros, right? So that's going to be, you said,
795,700 kilometers.
yeah. Oh, 700 or 7?
700.
Okay, so that's what we got. So 695,700, and then to make it kilometer to meter, I just put 3 zeros at the end? Is that reasonable? I'm going to use meters. You gave me an answer in meters, right, James? You gave me this number in meters?
So yeah, I don't even remember what that number is. It says R squared S, and then I put 1.5.
Well, let me point out what I want to point out. So this is what I'm saying. That number, 695,700,000, is 6.95 times 10 to the, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So here's what I want to point out. This number is on an order of 10 to the 3 larger in scale than this one is, right? 10 to the 11 versus 10 to the 8. So although I've been nagging you and saying use the radius, in reality it's probably not going to affect your answer as much. I'll tell you right now, on the test, I'll give you the distance from center to center. But I wanted you to just understand that concept, right? That it's always measured from center to center between the two objects. Yeah, because I realized when I was looking at the values, I'm like, it's probably not actually going to be significant. And you're going to square that number at the end. So it could have a small change in your actual force. So once you get the force to the left, we consider that to be negative. That's why this is right here, right? The force on the moon from the sun, because the sun is over here and the moon is here, is going to pull it left, so I'm going to put negative. Remember, this is net force now, not net torque. So it's not about rotation anymore. It's about left and right or up and down. And if the sun's here and the moon's here, it's pulling it left. That's negative. But the Earth is over here on this side. I'm pulling the moon to the right, so that gets a positive. We see what the net answer is to see which way this object will move. And what's the answer going to be? Which way is the moon going to stay?
Towards the sun.
Toward the...
I said 2.24 times 10 to the left.
Should be toward the Earth. If it were toward the sun, I think it would be an orbit around the sun. So the answer should be greater to the right. Let me see what actually... Do you have it in the back or not? 59? It does say towards the sun, actually, yeah. Interesting. So why does it stay in orbit around the Earth then, if the net force is toward the sun? They are both orbiting the sun. So they're both, I mean, the Earth is definitely being pulled around the sun.
The
But if
force
I-
of gravity mainly depends on mass and distance. Although the sun is bigger than the moon is closer to the Earth, the force of gravitational force on Earth is more than
Say that last part slower, James?
It says, why does the moon go around the Earth rather than the sun?
Yeah, what was the last part though you said? The very last sentence. You kind of mumbled through it. It seemed like it was important.
I don't know, it says 3 dots. It says the force of gravitational force of Earth is more than
It's more than the sun, it's going to say. Which is why it's odd that it's saying it, right? Maybe only at that position. Maybe only at that one position. At
Because
that,
the moon is much closer to the Earth than it is to the sun. Then there's like a longer answer. The gravitational force exerted by the sun on the moon is more than twice as big by the Earth on the moon.
oh. Yet it stays in orbit around. I got to think about that
I
more.
don't know. It's
But I mean, I understand what you're saying, but I want you to explain like with rationale or like some reason to it. You'll definitely have problems with exponents. You should know how to use scientific notation and calculus, for sure. Absolutely. Absolutely. I mean, G is in every problem, and that has scientific notation already. So you're going to have to use scientific notation no matter what. Okay? I'm not saying your answer will come out to that. Your answer will be 30 newtons, but you're going to have to use this in the process. Chris.
This problem was on the problem.
That's all right. What do you got?
312
Page 3.3.
Okay.
30.
323, number 30. Good question. Okay.
I got confused with not the new value. Like,
It's extraneous.
yeah.
That's the thing. So what the problem is all about is figuring out or realizing that what keeps a car in circular motion is the friction in the tires. So when we write these problems, if you remember, they're always this, right? We always start with the sum of FC equals mv squared over r, but the sum of FC is actually just ff. So there's no need to use the mu value in this problem, okay? There's no need. So the reason is, again, here's the car going around the track. Friction is always pulling toward the center every time. So there's no force acting outward, so it's not like ff minus something else. So ff is simply mv squared over r, and then calculate it. It's a great question, Chris. Okay, a lot of people came to ask me this, so if you didn't get this right, maybe jot that one down. Okay, this is number 30 on page 323. And you would ignore the mu value, actually, altogether, Chris. What you can...
What's the example where you would use?
Okay, I was just going to... You want me to follow up with either putting it there? So, if you take that mu value, okay, and multiply it by Fn, that'll give you the maximum static friction that the car can actually give back. So the idea is that this value that we're going to get as an answer better not exceed mu times mg, because mu mg will give the maximum FFS. Remember how the force of static friction is a variable force? It gets greater. So as I push on the desk, friction pushes back. I push harder, friction pushes back harder. So that maximum friction that it can push with until I exceed and it moves, that's what you'd be using mu to get. Okay? So you take mu times Fn, but Fn is just mg. So that's what you would use it for. But that would be like a part B to that problem.
Do our problem sets like get grade?
Your problem sets in this class? Yeah.
I don't see them.
Problem set 6 doesn't have grades on it. All the other ones should have them. Look at the older ones, James, yeah. From problem set 6, well, 6 is the only last one. But 7 is the one that you just turned in. So that one obviously doesn't have grades. If they're not, let me know, because it means that...
Yeah, but this is 5.
That means that I have to tell Gus to upload it. He probably I have all your grades for all of them, so I can tell you what your grade is. But if you didn't upload it back to your drive folder, it's probably not. There might be a second file in there. So look for the same name with the word graded after it too.
Oh, yeah, wait, I see one for 4.
So I tell him to upload 5. Other questions? We got like another minute or two. These are great questions, guys. This whole theory behind everything we've been talking about is really good. Let me think about anything else we didn't talk about. We talked a lot about torque, right? We had those couple problems there, which are great examples. Rotation equilibrium. Definitely know your labs. Your labs will both come up on the test. The last few labs. And then the 9-4, just make sure to know Kepler's 3 laws and understand where you're going to apply them. I told you the math, that'll come from that. Besides that, the rest is theory. Okay, the rest of Kepler's laws are theory questions.